Hi everybody. Today we'll be making the Dogstar right here in our lab. The Dogstar is a nickname for our brightest star in the sky, Sirius. Did you know that Sirius is a binary system, meaning that instead of one star, there are actually two stars orbiting each other. Sirius A is a bright main sequence star, while Sirius B is a dim white dwarf. It is also one of the most closest stars, and its blueness means it is very hot. In fact, blue stars reach about, 30,000 degrees Kelvin, which is 10 times hotter than the red dwarf star or a burning magnesium experiment. All we need for our mini Sirius is potassium chlorate as an igniting agent and oxidizer, starch, and Cupric Sulfate Pentahydrate. And also, you'll need an iron tray wrapped around in aluminum foil. The aluminum foil is here because iron becomes highly flammable due to increased concentration of oxygen. Aluminum, however, has a protective layer of aluminum oxide which prevents it from ignition. So, let's try making our mini Sirius. First off, we measure out 10 grams of copper 2 sulfate pentahydrate. Use the pentahydrate form because the anhydrous form of copper 2 sulfate has a different molar mass and therefore won't really correspond. Okay, next we have to add 15 grams of our fuel, starch. Now, as a quick side note, stars burn on hydrogen, not starch. Okay, so 15 grams of starch is put in. Now, let's put in our oxidizer and igniting agent, potassium chlorate. What potassium chlorate does here is that it helps us ignite our starch and also increases the oxygen concentration, meaning that it will make it easier for a starch to burn. This is because oxygen helps or supports combustion, meaning that it will help a fire burn more intensively. Okay. Next, let's get a stick and stir the components. Okay, so we have the mixture that will make our night sky glow. Now, when doing the burning part, do this in a well-ventilated area. See you in the backyard. Bye! Welcome back to my backyard. We'll use this tray to light up our night sky, or at least our backyard. Okay, so let's add the mixture. Now, let's use our blowtorch to light our mixture. Ready? Oh. Now, let's see the chemical reactions involved in the burning star. The first reaction was potassium chlorate's decomposition. Potassium chlorate decomposes at around 400 degrees to form potassium chloride and oxygen with the equation below. 2KClO3 becomes 2KCl and 3O2. This increases the concentration of oxygen in the mixture, which intensifies the combustion. Next is obviously the combustion of starch. As a disclaimer, however, this equation is only true if you assume that all of the starch's atoms have reacted with the oxygen. As I said in the starch video, starch is a polymer consisting of these atoms, in these very long chains at around 300 and 500 of these monomers. They react with 6N oxygen molecules to form 6N CO2 molecules and 5N H2O molecules. Then there's our colorant, copper 2 sulfate. Now, copper contains one electron in its valence shell. However, this electron and one electron on the inside was lost. But anyway, the intense heat of the combustion is absorbed by one of copper's electrons. This moves it to a higher orbital, meaning that it has more energy than this state. However, it's not really comfortable with this space, so it has to emit energy in some sort of form. And here, it chooses light. Copper 2 sulfate, in intense heat, releases blue light while the electron goes back to its original orbital. This reaction is extremely fast, and it almost instantly happens. Next, I will explain to you why I wrapped the steel plate with aluminum foil instead of just using the plate itself. Well, that's because even if iron and steel are flammable in current concentrations at around 21% oxygen, in higher concentrations, they may become highly, if not very highly combustible. For example, this is iron, while this is the higher concentration of oxygen. Iron will react with higher concentrations of oxygen to form these equations. This is iron 2 and this is iron 3 oxides. Because the reaction is quite violent, we don't want that reaction. However, aluminum is actually coated with its oxide already. This process is called passivation, where the coating is protecting the inside, which is pure aluminum metal, from the oxygen here. So, unless the layer is removed with something like acidic protons or chloride ions, aluminum metal is pretty safe against oxygen from the air. Thanks for watching, and see you in our next chemistry experiments and explanations. Bye!